I put together this review module to help with some of the harder calculations that you will face on the final exam. So this is certainly not everything that will be on the final exam, but I just wanted to put together some of the more challenging material, another example, another problem for you to work through at your leisure before the final exam. So the first problem, what is the change in entropy for the combustion of ethanol at 25 degrees Celsius, given the balanced equation of ethanol reacting with oxygen to produce carbon dioxide and water? So this is a summation calculation. So I would like to use the calculation of change in entropy equals the summation of how many moles and the entropy of products minus the summation of how many moles and the entropy of my reactants. And I provided those entropic values over here. All we need to do is plug those into our equation. So my entropy equals the summation of, well, my products are carbon dioxide and water. So I have 2 moles of carbon dioxide that comes with an entropy of 213.6 joules mole Kelvin, plus I have 3 moles of water that comes with an entropy of 188.8 joules mole Kelvin, minus the summation of my reactants, 1 mole of methanol at 282.7 joules mole Kelvin, and my 3 moles of oxygen, which come at an entropy of 205 joules mole Kelvin. Multiply everything through by moles, and moles will cancel out, right? I'm going to multiply this by 2, this by 3, this by 1, and this by 3, and then add and then subtract. So when I do that, I get an entropy that equals approximately 993.6 joules per Kelvin minus, from the other side, an entropy of 897.7 joules per Kelvin. Subtract those, my change in entropy for this reaction is 95.9 joules per Kelvin. Right, the biggest mistakes people make are dropping signs or forgetting to subtract when they're adding or adding when they're supposed to be subtracting. So that would be what I would check with these calculations. Make sure you're using the correct coefficients, right? The correct molar coefficients from the equation, the balanced chemical equation, and you're using the correct entropy or enthalpy values depending on the calculation that you're doing. So we see a positive change in entropy. Right, so based on that, that makes sense because I've got 1 mole of ethanol reacting with 3 moles of oxygen, and I end up with 2 moles of carbon dioxide and 3 moles of water, so 5 total moles. So I go from 4 moles to 5. There should be an increase in entropy, and that's what we determined. The next calculation, what is the change in enthalpy for the combustion of ethanol under 25 degrees Celsius? So we're going to use the very same calculation, except for instead of the summation of entropy, it's the summation of enthalpy values. So now the delta H equals the summation of how many moles and the delta H of each of the products minus the summation of how many moles and the delta H of the reactants. And again, I provided those delta H values. In an exam situation, I would just provide you with the values, the delta H or the entropic values or the free energy values for that calculation. So again, for our summation, I have 2 moles of carbon dioxide, and the enthalpy of that is minus 393.5 kJ per mole. Plus I have 3 moles of water at an energy of negative 241.82 kJ per mole, minus the summation of, I have 1 mole of ethanol at negative 235.1 kJ per mole. And then I don't have to worry about oxygen because the enthalpy of the formation of oxygen is 0. So again, I'm going to multiply through. And when I multiply through, right, multiply that by 2, moles will cancel. Multiply this by 3, moles will cancel. Multiply this by 1, moles will cancel here as well. And I'll get a delta H equals negative 1512.46 kilojoules minus a negative 235.1 kilojoules. So now I'm subtracting a negative. Again, remember, the largest mistakes, the biggest mistakes, the most common mistakes that people make are simply addition and subtraction for these calculations. So I'm subtracting a negative, which is the same as adding that across. So I end up with a delta H for this reaction of approximately negative 1277.4 kilojoules. So now I have my entropy and I have my enthalpy for this reaction. So the last step of this calculation now, we're trying to find the free energy of this reaction. I know the entropy, I know the enthalpy, and now I can determine the free energy. So what is the free energy change for the combustion of ethanol at 25 degrees Celsius? And we need the answers from step 1 and step 2. So from step 1, my change in entropy was a positive 95.9 joules per Kelvin. And from step 2, my change in enthalpy was a negative 1277.4 kilojoules. So now I can calculate the Gibbs free energy, where Gibbs free energy equals delta H minus T delta S. So two things I need to do before I do that calculation. Number 1, temperature needs to be in Kelvin. So Kelvin equals 273 plus degrees Celsius. So 273 plus 25 degrees Celsius, right? My temperature is 298 K. And then the second thing I need to do is I need to make sure that my enthalpy and my entropy have the same units. So I want to convert the units on entropy from joules into kilojoules. So I have 95.9 joules per Kelvin. I know that for every 1,000 joules, I have 1 kilojoule. So my entropy would be 0.0959 kJ per Kelvin. Now I can calculate my Gibbs free energy. So delta G equals negative 1277.4 kilojoules minus 298 times 0.0959 kilojoules per Kelvin. So when I multiply, Kelvin cancels out, and then I can subtract, and I'm going to get a delta G for this reaction of approximately negative 1,306 kilojoules. So yes, this reaction is spontaneous because I have a negative delta G. The reaction is spontaneous. We can also look at that with respect to delta H and delta S, right? We've got an exothermic reaction. Reaction is exothermic, and we know increasing the temperature increases the entropy of the system, and we have a positive delta S, so we have an increase in entropy during the course of the reaction. So the reaction is exothermic, which helps us, and results in an increase in entropy. Both of those things are favorable, so you put them both together, you are always going to get a spontaneous reaction. Any reaction that's exothermic and results in an increase in entropy will always, always, always be a spontaneous reaction. This question involves a few different steps. So we're given the information that ethanol has a boiling point of 78 degrees Celsius, has a freezing point of negative 114 degrees C. How much heat would be required to convert 56 grams of ethanol at 32 degrees Celsius into ethanol vapor at 95 degrees Celsius? And then we're given the enthalpy of vaporization, the specific heat of both liquid and gas phase ethanol. So we need 3 different calculations here because we need to map out basically the temperature transition that we're doing and the process for each of those temperature transitions. And so to write that out, we have 56 grams of ethanol at 32 degrees Celsius. So we have a liquid at 32 degrees. I need to warm that up to 78 degrees because that is the boiling point of ethanol. And then I'm going to go through a phase transition where I go from liquid at 78 degrees to then gas at 78 degrees. So that's a second transition with a second separate calculation. And then once I've gone through that phase transition at 78 degrees, then and only then can I continue heating that sample of gas all the way up to 95 degrees Celsius. So I'm going to have the ethanol in the gas phase at 95 degrees. So we need to know the temperature change for each of these transitions. So our first temperature change, I go through 46 degree change there. Here's a phase change, so there is no temperature change, right? It's isothermic. And then the last one is a 17 degree temperature change. So as I said, 3 separate calculations. Calculation 1, 2, and calculation 3. Calculation 1, I need to use Q equals MC delta T, where C will be the specific heat of liquid ethanol, because I'm taking a mass of 56 grams of ethanol and I'm changing it from 32 degrees to 78 degrees Celsius. So I want to find that heat. So Q equals, I have 56 grams of ethanol, and the specific heat is 2.3 joules gram degree Celsius, and it's going through a 46 degree Celsius temperature change. So multiply that all together, and I get approximately 5,924.8 joules of energy are going to be required to heat that 56 gram sample of ethanol 46 degrees Celsius. Calculation 2 is a phase change. And for there, I need Q equals the number of moles times the delta H of vaporization. So I need to find out how many moles of ethanol I have. Well, I know moles equals grams over molecular weight. I have 56 grams of ethanol, and ethanol is 46 grams per mole. I have approximately 1.217 moles of ethanol. So Q equals, I have 1.217 moles of ethanol, and the heat of vaporization is 38.56 kilojoules per mole. When I calculate through, right, moles cancel out, and I'm going to be left with approximately 46.94 kilojoules of energy for step 2. Now I need step 3, and for step 3, I'm back to Q equals MC delta T, except for I want to use the specific heat now of ethanol vapor. Because now I've gone through the phase change. I've gone from liquid ethanol to ethanol in the gas phase. So I can find that heat. Q equals, it still weighs 56 grams, so that didn't change. What did change was the specific heat. Now I've got a specific heat of 1.4 joules per gram times degrees Celsius. And my temperature change, my second temperature change is 17 degrees Celsius. So that heat is approximately 1,332.8 joules. Now to find the total heat, right, that's what I'm looking for, the total heat, I need to add all 3 of these steps together. And before I can do that, I need to convert step 1 and step 3 into kilojoules. So step 1, 2, and 3. Step 1 is approximately 5.9248 kilojoules. Right, I'm going to divide all of these by 1,000. Step 2 is 46.94 kilojoules. I didn't have to do anything to that. And step 3 would be approximately 1.3328 kilojoules. Add all 3 of those together, and I would find out that this entire process would take about 54.2 kilojoules of energy. Be aware of the different calculations needed for each step, right? If I'm heating one phase, that's Q equals mc delta T, because the specific heat is tied to that phase of the substance. If I'm going through a phase transition, right, there is no temperature change. It's just the energy required to go through that phase transition per mole of that substance. And for the third calculation, we're back to just heating everything in that vapor phase. So again, we're back to Q equals mc delta T. But we need all 3 of those steps, where the calculation for each step is a little bit different because we're going through 3 different processes during the entirety of that transition. For this question, we have a solution of vinegar that's 6% volume by volume, acetic acid and water. What is the molality of this solution? And to make our lives easy, let's assume the solution is a 1 liter solution and that the density of acetic acid is approximately 1.05 grams per milliliter. So a 6% volume by volume solution means that we have 6 milliliters of acetic acid for every 100 milliliters. So that means we have 94 milliliters of water. So if we magnify that over the entire 1 liter solution, right, multiply both of those by 10, I have 60 milliliters of acetic acid in approximately 940 milliliters of water. Why is that important? That's important because we're asked to calculate molality, and molality is moles over kilograms of solvent. So we needed to find the volume of our solvent so we could find the mass of our solvent. And I also needed to find the volume of our acetic acid because I need to find moles of acetic acid. So step 1, we're going to find moles of acetic acid. So I've got 60 milliliters with a density of 1.05 grams per every 1 milliliter of acetic acid. So approximately 63 grams of acetic acid. Look up the molecular weight of acetic acid. It is 60.05 grams in 1 mole. So we can turn those grams of acetic acid into approximately 1.05 moles of acetic acid. Now I want to find the mass of my solvent. So I have 940 milliliters of water, and you should know the density of water is 1 gram per 1 milliliter. So I have 940 grams of water. I need that mass in kilograms. So for every 1 kilogram, we have 1,000 grams. I have 0.94 kilograms of water. Now we can find molality. My molality equals 1.05 moles over 0.94 kilograms of solvent. My molality for this solution is approximately 1.12 molal. For part 2, what would be the freezing point of this solution? For that calculation, we need our delta TF equals negative I KF times our molality. Our change in freezing point equals our negative Van Hoff factor times the freezing point constant times the molality of this solution. So my change in my freezing point will equal, well, my Van Hoff factor for acetic acid. Acetic acid is molecular, so it's going to have a Van Hoff factor of 1. My freezing point constant for water, 1.86 degrees Celsius per molal, and my molality, 1.12 molal. So when I multiply, molality cancels out, and I'm left with degrees Celsius, and that's good because I'm looking for a temperature. And so my change in temperature of the freezing point would be approximately negative 2.7 degrees Celsius. So I would expect this solution to freeze at approximately negative 2 degrees Celsius. We could do that calculation based on this volume by volume concentration. We had to take that volume by volume concentration, turn it into actual volume, and then use density to find the actual mass for both of those components in this 1 liter solution. I wanted to review some of the rules for our simple nomenclature of alkanes, alkenes, and then a substituted alkane. Step 1 is always find the longest carbon chain. So if we take a look, here's my longest continuous carbon chain. Dip down here and then loop that back around. Now we want to number that chain in the way that brings us to the first branch with the lowest number possible. And if I go up here, I number this as 1, 2, 3, 4. My first branch is on the 4th carbon. If I number it from the right, I have 1, 2, 3. My first branch is on the 3rd carbon. So I want to number this from the right side. So I've erased those other markings, and now I can continue on numbering this hydrocarbon. So this would be carbon 4, carbon 5, 6, 7, 8, and 9. So 9 carbons, and it's an alkane, so something, no name. After that, we want to see the branches I have off of this carbon, right? We want to find and number our branches. So let's start from the right side. On the 3rd carbon, I have a methyl. On the 4th carbon, I have a methyl. On the 5th carbon, I have a methyl. And on the 6th carbon, I have an ethyl group. So putting that all together, I would have 6 ethyl, 3, 4, 5, trimethyl, nonane. Quite the long name, but it basically tells us I've got a 9 carbon alkane, that I have an ethyl group on the 6th carbon, and 3 methyl groups, one on the 3rd, the 4th, and the 5th carbon. Remember, when we're putting these, we alphabetize these based on the name of that branch. So E comes before M, so ethyl group comes before methyl group in the naming. Here's a simple alkene. Steps are still the same. Our first step, longest carbon chain. And we have an alkene present, so the longest carbon chain that contains our double bond. All right, here is our longest continuous carbon chain, and I want to number this from the side that gets me to the double bond or the lowest number possible. So carbon 1, carbon 2, carbon 3, 4, 5, 6, 7, and 8. So I've got 8 carbons, which is oct. I have a double bond on the 3rd carbon, so oct 3-ene. Tells us I have an 8 carbon hydrocarbon that has a double bond on the 3rd carbon in. What else do I have, right? I want to find the branches off of this. So on the 2nd carbon, I have a methyl group. On the 6th and 7th carbon, I also have a methyl group. So putting that all together, I have 2, 6, 7 trimethyl oct 3-ene. And then there's one more thing I can add to this. What is my arrangement, right? I have geometric isomers for alkenes. I have specific arrangements. What's my arrangement around this carbon-carbon double bond? And I notice that both of the carbon substituents are on opposite sides of this carbon-carbon double bond. That is a trans relationship. So I have a trans alkene, opposite side of the carbon-carbon double bond, with a methyl group on the 2nd, the 6th, and the 7th carbon in that chain, right? And the double bond is the 3rd carbon in on that chain. This last example is a substituted alkane. Now the alcohol takes precedent. I want to find the longest continuous carbon chain that contains the alcohol. So step 1 is still very much the same. Longest carbon chain. And I've drawn it in a way that's pretty easy to identify the longest continuous carbon chain in this case. And now I want to number this in a way that gets me to the alcohol with the lowest number possible. So I'm going to number from the left, carbon 1, 2, 3, 4, 5, and 6. So I've got 6 carbons long, so that's hex. And it's an alcohol, and the alcohol is on the second carbon. So hexane, 2-all. Telling me I've got a 6-carbon hydrocarbon where an alcohol is present on the second carbon. Other branches off of this, I have a methyl group on the second carbon as well as that hydroxyl group, and on the fourth carbon, I have a methyl group. So putting that all together, I have 2,4-dimethyl hexane 2-all. I have a 6-carbon hydrocarbon that has an alcohol on the second carbon and a methyl group on the second and the fourth carbon. Those steps are going to be very much the same. We want to find the longest continuous carbon chain that contains our functional group of interest. We want to count that in a way so that our functional group has the lowest number possible, whether our functional group is a carbon branch, a double bond, a triple bond, or an alcohol, or a ketone, and depending on some of the other substituents that we looked at. And then we want to number the remaining branches off of that carbon chain, and then put those together in alphabetical order to determine the overall name of this structure.